Yeah. Come on in.
It's warm up here.
Hello.
Hello.
How are you, Angelina?
I'm wonderful. How are you, Mr. Dutton?
I'm doing well, thanks. Oops. Hey, DJ, how's it going?
Good, you?
I'm well, thanks.
Good.
Go ahead, go to that link and do the survey while we're waiting for folks. How's it going, Vivian?
Pretty good, I guess.
All things considered.
All things considered. Haven't left the house in like 3 days. It's great.
Yep, join the crew. All right, Aisha, Victor, Isabella, welcome. Good morning.
Good morning.
Please go ahead and do the link, the survey that I have linked there. So, there I am. How's it going, Julio?
Good.
Good to see you. Make sure you do the survey.
Okay.
I feel like I should go get my phone and walk into your class.
How's it going, Christian? How's it going, Laviana?
What?
Device audio.
With that many windows open, it can be a little tricky.
Oh, so I was gonna go get my phone so I can.
Oh, I mean on the computer. Just to like navigate through everything. Pixel 3. Who's Pixel 3? Whose name is Pixel 3? All right, so we have a special guest today. You're not on yet.
I'm not.
Say hi to Miss Danita.
Hi, guys.
Hi.
How's it going?
Fine.
So we're gonna do a lab today. That's why I have this up. We've got 12 12 out of 20 kids. So make sure you do that. Make sure you do that survey. That'll really help me out. Once you've done the survey, then open up the number 87, which is the lab we're going to be doing remotely. I don't have to have the keyboard. Oh, someone left. Who needs more time for the survey? Respond in the chat.
Are we gonna fill this out like together?
Oh yeah, we're gonna do the whole thing. I'm gonna, well, Miss Anita and I are gonna do the whole thing, and you guys are gonna record the data. Yep.
All right.
All right, so if you still need more time to do the survey, please at some point before the end of today, get that in so that I can make some decisions around spring break, and also just generally get your feedback. What we're gonna do today is we're gonna put off the rest of the test, correcting the rest of the test until tomorrow, because I wanted to take the time today to do this lab. I will be doing the lab here with my very lovely assistant, Miss Danita, and we will be collecting the data together. If it goes too quickly, you know that it's always going to be on YouTube later, so that you can always check it out later. But just try to record and feel free to speak up. I'm going to be away from the computer for the most part, but try to record all the data as it comes through, and make sure that you have number 87 open so that you see what we're actually doing. So let's quickly go over the materials. Does everyone have 87 open?
Yeah.
All right. So are you seeing the video, or are you seeing the document right now?
Document.
Okay. Fix that. Now you're looking at the video, right?
Yeah.
Awesome. Okay, so what are the materials? What are the materials that we need for this lab?
A meter stick.
All right. Unfortunately, we have a ruler. But I already measured this out. All right. And I also have tape measure. Okay. What else?
3 solid ball bearings or marbles of different sizes. A board that's 1 meter long.
All right. So here's our marbles, 3 different sizes. And we see that the board is marked. Here's the 1 meter mark. The 0 meter mark is right off camera. We can actually lower the camera a little bit to show that. And I've got 0.75 meters, 0.5 meters, and 0.25 meters. All right, what else?
3 unopened cans of different diameters with non-solid.
Okay, we have all sorts of cans going on here. So this is a can that I put some water into. So the water is sloshing around. And apparently it's walking too. Here, this is an empty can. Top and bottom are taken off. This is another empty can, but it's much smaller. Here is a full can. Ooh, tomato paste, yum. This is another full can. This is, I stuffed some socks into here, so it's not very dense, all right? But it is full and it's uniform. So in other words, there's no point in this can that has much more mass than any other point, except for the outside. And then we have 2 full cans. This is coconut milk, and so it's pretty liquidy. This is some diced tomatoes, which is fairly solid. It's not perfectly solid, but it's fairly solid. So there's going to be a difference in how these 2 things rotate. Yep, and then that is in comparison with the tomato paste, which is also solid but smaller. All right, what else?
The timer.
Yeah, a timer.
What?
A timer.
A timer. So, through the magic of technology, I will be timing here. It's going to be really difficult because of probably the latency on the, the camera in order for you to time. So we will report times from here so that you can record them. All right, my stopwatch is all set, and we'll be doing the recording. We also have some other objects so you can see how things roll down this ramp and how they roll down differently from each other. So I've got baseball, tennis ball, lacrosse ball, that's the red one, and then the orange one is a street hockey ball. Now the difference between these, a baseball is solid all the way through. Lacrosse ball is also solid all the way through. And the difference is that these 2 are actually hollow. The street hockey ball, you can hear it bouncing on the board, and the tennis ball is also hollow. So you're going to see that there's some patterns going on here. So what do we do next in this lab? What's our next step?
Well, I have a question.
Yes, Layla, go ahead.
What is rotational inertia?
And that's what we're going to be discovering. So there's a little blurb about that, but as things rotate, they have inertia that keeps them rotating. For example, Frisbees. So I have a collection of Frisbees here. This is from back in my college days. We were the Fighting Gobies. And so this Frisbee, you know that when you throw it, right, then it rotates. all right? And it keeps on rotating. It spins throughout the air the whole time, and it has this rotational inertia. Now, we see that there's similarities between all of these Frisbees, even this fabric one. You see the rim is built up on the fabric one. So what is a similarity among these Frisbees? What helps them maximize what's called their rotational inertia?
Oh, okay.
The wind.
Say it again, DJ.
The wind.
Well, wind, absolutely. It needs air pressure, right? The air has to push up on the Frisbee itself. Okay? But why does it keep spinning?
Because it's got the little like lip rim thing.
Excellent.
Right?
Yep.
So does it like trap wind under it and it just keeps circulating?
Yeah, so it actually serves two purposes. Not only does it trap air underneath, and so it's kind of it has a little pocket of air underneath, but you have more mass on the outside, which gives the object itself more rotational inertia. So the more mass that's on the outside, the more it wants to keep spinning. Remember, inertia, an object in motion stays in motion unless acted upon by an outside force. And the more mass something has, the more inertia it has. So the more mass that's on the outside, then the more inertia that it's going to have as it's spinning. Okay, so these are some good visual aids for you to keep in mind as we're doing this lab and understanding what it is that rotational inertia is. Because as things spin around, the more mass that is on the outside, the more rotational inertia it's going to have, and that's going to help you explain some of the phenomena we see today. All right? Good question. Other questions? Okay.
Is rate of rotation like a calculation, or is it just like?
Yes, absolutely. For this lab, we're not going to be worried about the rate of rotation because if I roll, for example, a baseball down this ramp, if you know the circumference of the baseball, then, and you know, like, what the distance is, you know that it's 1 meter, then you could actually calculate how many times it rotates as it goes down the ramp. And based on that time that it takes it to roll down the ramp, you could actually calculate how many seconds it takes for each rotation. And so that's a measurement of rotational velocity, and we could even calculate rotational acceleration. But that is not for this lab because that's going one step further than we're going to go in this lab. Really, we're going to be comparing the rotational accelerations and rotational velocities of these different objects. So, for example, I've got two solid objects here. And if I roll them both down from the 1 meter mark, or right before the 1 meter mark, then we see that the lacrosse ball, it actually hit the webcam a little bit, but the lacrosse ball went down a little bit faster than the baseball did. All right, and you may notice that there is a size difference between the two of them that may actually impact the difference. If you could hit save. All right. Just a second. Okay, and then we see with the tennis ball and the lacrosse ball, remember both of them are hollow. The size difference is almost negligible between the two of them. And if we release them down, we see that the lacrosse ball is going a little bit faster. So that tells us that there is some difference in rotational energy. The tennis ball, I can tell you this, that there's multiple layers to the outside of the tennis ball. There's a rubber, and then there's that cloth outside, whereas the street hockey ball is this hard plastic shell. And so most of the mass is actually concentrated more towards the outside, whereas with the tennis ball, it's got a thicker outside layer, and so the mass is distributed among that thick outside layer. So the street hockey ball actually has a little bit more rotational energy. Right? Not very much, but a little bit more. So this gives you an idea of what we're talking about before we get started. Go ahead.
So we're supposed to hypothesize about which can would go down would have the most. I'm confused.
Yes, ma'am. For each situation, I want you to make a hypothesis about what is going to go faster and why.
Wait, where are the... Okay, never mind. I understand now, I think.
Okay. No, that's no problem. And so what's the next step?
I don't know.
All right.
You
Well,
start at the lab?
yep, next step, the lab.
Oh, okay. You do the first, you make the ramp. Is your ramp at 15 degrees, incline of 15 degrees?
That's a great question. How would I determine if my ramp is at 15 degrees?
You take the length of the ramp and then how high up it is.
All right, so let's all record this together. And
Okay.
I'm committing a mortal sin right now. I am measuring in inches because unfortunately I do not have metric at home. All right, so you're gonna have to forgive me. But the length of the board is 45 inches.
45
All right, and then from the ground, one end of the board is 26 inches off the ground, and the other end of the board,
At the feet mark.
the whole length. I just took the whole length. The other end of the board is 36 inches off the ground.
Wait. Why are there two legs?
So remember, it's at an angle, so we have to make a triangle from this. So the hypotenuse of our triangle, what did I say the length of the board was?
45 inches.
45 inches, right? It's really hard to say inches. I just keep wanting to say centimeters. And then I said the height of the lower end of the board was how many inches?
26, I think.
26. And the height of the higher end of the board was
36.
36. So your hypotenuse is 45 inches. And the height, this measurement over here, from horizontal is 36 minus 26, which is how many inches?
10.
Beautiful.
So do I just put, okay, I don't know how to word that. But okay, go ahead, continue.
So you can sketch out that triangle. This is the opposite length right here. The opposite length was 10 inches. The hypotenuse was 45 inches.
Right.
And from there, you can come up with an angle using your trigonometry.
That would be...
I'll let you do that on your own. How's that? But it is pretty close to 15 degrees. I tried to get it pretty close to 15 degrees. All right, so what's step 3? Make sure you have all that recorded. I'm taking advantage of the fact that I've got Miss Danita here.
Select 2 marbles or bearings and predict which of the 2 will hit the ramp first. I mean, will hit the bottom of the ramp first.
All right. So what do you call the big one? What's it called?
A marble.
Is it the shooter? Okay. So got the shooter here, and I've got just kind of your standard marble here. All right. So big one and a small one.
Ooh.
I'm gonna hold the ruler at the top, That's going to prevent the marbles from rolling down until they will do so at the same time. And then I'm going to count 3, 2, 1, go. On go is when I'll release.
Okay.
So 3, 2, 1, go. I screwed up. Are you ready?
Yeah.
3, 2, 1, go. All right, which one won?
I don't know.
If we can.
Anyone see that?
Looks like the one on the right.
The small one or the big one? It looked to me like the small one won, and it took 1.2 seconds for the small one to get to the bottom.
Okay. So, small marble, big marble.
Wanna do it again?
Yeah, let's do another trial.
One at 1 point. How long? 1.2 seconds.
Took 1.20 seconds. Really significant figures would be 1.2 seconds.
Okay, so I'll take out the 0.
All right. So let's do it again. 3, 2, 1, go. That looked pretty close. So that time it looked like they both hit at about the same time. So 1.3 seconds.
Oh, versus big marble. It was a tie. Are we gonna do it again?
Yep. One more time, because in science we love to use the rule of 3. 3, 2, 1, go. Did it look like a tie again?
Yeah.
No,
No?
No, I don't know.
that look like the one on the one on your left. Wait, no, on your right. I mean, on your right.
Oh, that was the big one. Okay.
Mm-hmm.
So 1.3. That was 1.3. So it seemed mostly like 2 out of the 3 trials, it seemed inconclusive, right? Didn't look like the big one or the small one actually went down very much faster. But that took 1.3 seconds, that last trial.
Well, at least they all took the same amount of time. Almost.
Is there a time for the larger marble for like the first trial we did, or are we just gonna leave that blank?
Let's just say that it took greater than 1.2 seconds.
Okay.
There's a lot of potential error in here. So the time is less important than the qualitative observation of which one seemed to go down faster.
Oh.
All right.
Oh, let's.
Yes, DJ.
Never mind. I'll wait till later.
Okay. So let's do number 5.
5.
What are we doing for number 5?
Repeat the process with 2 hollow cylinders.
Okay, so we've got tomato paste and, I don't know, what was this, kidney beans?
I don't know.
All right. Lots of beans. Lots of beans.
Do you just collect empty cans?
Yeah. I had to pull them out of the recycling last night so that they didn't get recycled this morning. All right. See, all of these things are things that you can do at home too. All right, make your predictions.
The big can will win.
I think the smaller one.
Okay, write down your predictions.
Oh, wait, we're supposed to write that down.
Yeah, predictions are really important.
Wait, where does that go?
Wherever you want it to go,
Okay.
as long as you keep yourself organized.
Okay.
Which one is it? Is this the 4 or number 5?
This is number 5.
Number 5? Okay.
Okay, I'm ready. What is that? white thing right there.
This is a TV
No,
box.
not
Oh,
that.
this is a kitchen scale. So
Oh.
if we want to make some mass measurements, we can measure the mass of these objects.
Oh, okay.
That's a door.
Oh wow, never seen one of those.
All right. Are you ready?
Yes.
All right. 3, 2, 1, go.
Oh, my camera.
Like the smaller one.
It did look like a smaller one, didn't it?
Smaller one definitely won.
So, let's switch around. Which one is on which side? See if that makes a difference.
Do you want the number?
Yeah, and the timing was what?
1.46 seconds.
All right, so we don't really have enough significant figures to count hundredths of a second. So what does that round off to?
1.5.
Awesome.
Excuse me, was the small one, was it empty or full?
It was hollow.
These are both hollow. These are both empty.
That means for the bigger can, we'll just say greater than 1.5.
Yeah.
The
But
smaller can.
really the lesson here is that these are taking longer than the marbles did, right?
Mhm.
Yeah, because they have more mass, right?
I am going to not answer that question. I know, I'm being difficult.
Excuse me, the time for the smaller one was 1.5.
The time for the first can to go off the edge was 1.5.
Okay.
All right, you guys ready?
Yeah.
No.
3,
No.
no.
Okay, I'm ready.
Okay, 3, 2, 1, go.
Okay, yeah, the smaller one.
Yeah, the smaller one definitely won.
And that was at 1.6 seconds.
Oh, jeez, Louise. Small versus big. I'm just gonna assume this.
All right,
I'm ready.
so that's all we're going to do for the hollow cylinders. I do not have,
Oh, okay.
do I have a third? I don't have a third hollow cylinder. Oh, yeah, third trial.
Yeah, I was like,
Thank you, Miss Anita.
Hmm?
See, she's got your back. All right.
Just get it closer to you. They
They
go
roll
off
that
the
way.
side.
Yeah. All right. 3, 2, 1, go. Woo! Look at that one.
Like a tie.
It did look
Mine
like
lagged. I didn't know who won. Mine lagged.
that was 1.7 seconds. So I think that you could make the argument the smaller one is rolling down faster and that one was an outlier because, and that's again why we do 3 trials, because there's a lot of error in this. But I definitely did see the smaller one roll down faster. They did try to get in a fight with each other.
yeah, the big one was tired of losing.
Yes.
And kidney beans just get a bad rap.
Probably because the name is kidney beans.
Okay, so next up, we'll do number 6, which is 2 cans with non-sloshing contents. All right, these are relatively solid cans. Tomato paste doesn't slosh around, and socks in a can do not slosh around.
Flash like liquid.
Yep, sloshing would be like liquid.
Okay, let me write it. We need to write which will win, right?
Yep.
Do we have tomato paste can and what?
Sock can.
Sorry, I'm just making an advertisement. We got a tomato paste can, and we have a can full of socks.
Okay.
That is the scientific term for this. Can full of socks. Sock can.
Mr. Dutton, you're wearing pants today, not shorts. What happened?
All right. Are you ready? Did you make your
Oh.
predictions?
Okay.
All right. Instruction. I'm going to start rolling. 3, 2, 1, go. What?
Wow.
Oh, it's 4-1-1.
That was 1.5 seconds.
1.5. Okay.
Where did I have? The tomato paste was on the left.
That was 1.7
1.5.
or 1.5. Okay.
Someone is having a slap fight.
Oh, sorry.
Oh, no problem. Just curious as to what was happening. All right. Trial number 2. 3, 2, 1, go. Pretty consistent results, huh?
Yes.
Mm-hmm. What time was that?
1.68 yellow.
All right.
One
Oh,
point.
you did
I
the
tried.
nice. So Miss Danita is stepping up her science game. She got 1.5 for the small one and 1.7 for the big one.
Wait, 1.5 for the small one, 1.7 for the big one?
Yep.
Oh, wait, 1.5 for the small one again?
Yep. She got
So
time.
1.5 for a tomato?
1.5 for the tomato paste. 1.7 for the can o socks.
Oh, no.
Oh yeah.
1.7.
Okay.
You ready?
No.
What?
No.
All right. I'm gonna go in 7 seconds.
Okay, I'm ready.
3, 2, 1, go.
I hope those don't bust on your floor.
No, they're just hitting the tripod that the webcam is on. What was it?
1.06 seconds and 1.26.
Whoa, that one was
Yeah.
a quick one.
Yeah.
All right. So there might be some error in there.
Yeah.
So 1.1 and 1.3.
Only one dove off the side.
One did dive off the side, yes.
Uh, 1.1.
We always
So-
get that weird outlier. Man.
1.3. How is that possible?
There may have been some,
Human error.
yeah. There's always some human error in all of these measurements. So that's why we do through the 3 trials in order to see which one we can really rely on. And just out of curiosity, because you may or may not want to include this in how you report your results, but this tomato paste has a mass of 201 grams. That part I can do metric. And the can o socks has a mass of 139 grams.
Wait, tomato.
201 grams, 139 grams.
This is all going in recording, right?
I think that's worth recording because that might help you explain why the tomato paste went down faster.
139, you said, right? For sock?
139 for this guy and 201 for this guy.
Wait, but we didn't get the measurements for the other things.
I will say this, it is less important that you have the total mass of the other ones that we just did,
Okay.
all right? That might help you explain why there was a difference between these two.
Oh, okay.
So, next up we're gonna do one of the hollow cylinders and one of the solid ones.
Okay.
Yep. So we're gonna take the full tomato paste and we're gonna take the hollow tomato paste.
That sounds pretty bad.
Make your prediction. Which one do you think is gonna go faster?
The hollow one.
The one with more math.
And I'm gonna go in 3, 2, 1, go. That was the solid one that won.
Oh, no.
1.29 and 1.52.
So 1.3 and 1.5. 1.3 for the solid, 1.5 for the hollow.
Where is the...
This has been brought to you by Campus International High School.
Wait, it was 1.3 and 1 point what?
1.3 and 1.5.
Okay, this follow.
All right, trial number 2. 3, 2, 1, go.
One point two, 1.4.
Thank you, Miss Danita.
You remember which was which?
The solid one was 1.2. The hollow one was 1.4.
Hmm.
All right. One more. Okay, so if I cut out a little bit, I apologize. I think we may have someone else streaming on our internet connection. Okay, so 3, 2, 1, go. What was that?
1.6, 1.26.
Okay, so the solid was 1.3 and the hollow was 1.6.
Sorry, 1.1.
Oh, 1.1 and 1.3. Sorry about that. 1.1 for the solid, 1.3 for the hollow. And we're not going to do 3 trials of this one, but just to drive home the point of solid versus hollow, we're just going to do this one real quick. We're not even going to time it. We're just going to make some qualitative observations about how this one works out. You don't have to record it, but what is your prediction about how this is going to work?
The one with more mass will win. He's
All
going
right.
down faster.
So let's take a look at how this goes. Yep, prediction bared out. So we can see that there is some consistency between having this solid cylinder and the hollow cylinder. So let's take a look at the comparison between a solid cylinder and a solid ball, a solid sphere. So if you're following along at home, I'm on number 8. Okay, this baseball has a mass of 145 grams. The cylinder, the tomato paste still has the same mass of 201 grams. Again, the baseball is at 145 grams, and the cylinder is at 201. Now, there is a potential issue with the baseball, and that is it has seams. And so when it rolls down, you can even hear that it bumps along those seams. So that creates a little bit more resistance. All right, so I'm gonna, now that I'm thinking about it, I'm gonna trade this out for the lacrosse ball. And I believe the lacrosse ball is actually the same mass. So shouldn't change anything. And of course it doesn't want to stay. I'm getting around 141. So 141 for the lacrosse ball.
Is that cylinder the same tomato paste?
It is the same tomato paste.
Okay.
So make your predictions about which one is going to go down first, the sphere or the cylinder.
Sphere.
I hear a vote for sphere.
Yeah, I think the ball will go down faster.
All right. 3, 2, 1, go.
You were right.
So whoever said ball, from trial 1, it looks pretty good.
What was the time?
1.2 to 1.4.
So that was 1.2 for the ball, 1.4 for the cylinder.
Okay, I'm ready.
All right. Trial number 2. 3, 2, 1, go.
Whoa. Those are very close.
That was very close.
The ball won.
I think the ball won by a little bit, but
1.13, but I think I had a lag and a lapse.
okay. So let's call it 1.1 for both. I don't think one side of this board is faster than the other. But I think it was mostly me not raising the ruler in time. I'll be aggressive this time. All right, starting trial number 3. 3, 2, 1, go.
Yeah. Jeez. 1.05 and an additional 0.24 for the second.
So both of them were at 1.1.
But does it say which one you won?
Oh, you said not 0.024, 0.24. Oh, so that would be 1.1 and 1.3. Yes. 1.1 and 1.3. All right, we're almost done. Thanks for hanging in there. I know this is a little bit longer than you anticipated. So let's compare the lacrosse ball to the hollow tomato paste. The hollow tomato paste has a mass of 24 grams.
Wait, say that again?
So we're going to compare the solid ball with the hollow tomato paste, and the hollow tomato paste has a mass of 24 grams, somewhere between 24 and 25. Go ahead and make your predictions.
The lacrosse ball won. Ball won.
And we're going to go in 3, 2, 1, go. Woo! Woo!
Okay.
That wasn't even close.
No. 1.1, 1.4.
The ball won at
1.1, and the cylinder was 1.4.
okay.
All right. Trial dose. 3, 2, 1, go.
One point two, 1.6.
1.2, 1.6.
It's not as quick to push the left.
And last trial for this combination, and then we'll start sloshing. 3, 2, 1, go. Oh, there was some human error on the release there.
1.2, 1.5. So 1.2 for the lacrosse ball, 1.5 for the hollow can.
Okay, last one. Good job hanging in there. So here I've got, this has water inside. This has the potential to be very messy. Hopefully it will not be messy. I do not want to have to be drying the floor of my office up. All right, so Miss Danita's laughing.
Yeah, huh?
This is what happens when you do science at home. Sometimes it gets messy. All right, the mass of the can with water in it is 306 grams.
Ooh.
And the mass of the can with the, it's just diced tomatoes, so it's non-sloshing, is 481 grams.
481.
Doesn't slosh it. All right. We may only get one trial out of this.
Make it tape it. All right. In the name of science.
Betting on the can like on board.
All right, make your predictions. Sloshing or non-sloshing?
Sloshing.
3, 2, 1, go.
You were wrong.
No spills.
0.98
What was
seconds,
the time?
and then an additional 0.34 seconds.
So 1.0 and 1.3. Trial number 2. 3, 2, 1, go.
1.3, 1.7.
Okay, so let's take a second and talk about, well, record that 1.3 and 1.7. But what did you see happening? This is probably the most interesting out of all the trials. What did you see happening as both of these were rolling down?
They was colliding with each other.
There might have been a little interference. I agree. There was something else that was happening, especially with the one with water in it.
It was rocking.
Nice. So the water inside was moving and was countering the entire inertia of the can itself. All right. And if you saw the first trial, it was beautiful. The first trial, this can just kind of stayed here for like 1/10 of a second before it started to move because of all of that inertia of the water inside. So there's a lot of interesting things that happens when you have sloshing contents like this.
Slosh.
We're getting a little bit of leaking.
Ooh,
So I'm just going to not do trial number 3.
thank you. Or, well, it's only a second, so if it just goes quickly.
I'm just going to not take any chances.
Okay.
And I'm going to replace the one with water with the one with coconut milk. All right. So you can hear that's pretty liquidy. It's not going to be the same as the one with the sloshing water. This is a mass of 468 grams.
468 grams.
Someone's all late. All right, so let's do this last trial just to see if the coconut milk behaves in the same way that the water did. 3, 2, 1, go.
Oh,
It did not.
not at all.
Coconut milk. Wow.
It also hit radio.
I think we saved the laptop.
Save the laptop though.
So that was 1.15, and this was an additional 0.27.
All right, 1.15. And so that would be 1.2, and this would be 1.4. 1.42. It turns out to 1.4.
Oh, you added that. Got it.
All right, so there seemed to be some sort of impact on this being full of a sloshing liquid versus being only half full, because the other can, my leaky liquid can, is only half full of water. All right, so that seemed to have some.
Would it be more tightly compacted and more dense?
Yeah, absolutely. This is way denser because it's the same volume, and remember, this has a greater mass.
So maybe it's not mass, it's density.
I will give you some guidance here, and it's a lot of different things going on here. But remember, we're looking at the rotational inertia. So where is the mass? Is it focused in the middle? Is it focused on the edges? Is it evenly distributed? And so you can make the argument that this one is evenly distributed, whereas this one is unevenly distributed, and it changes over the course of the run. All right, so there's a lot going on here. As you answer those analysis questions, which is something that I want you to start on today, and then you can we can finish together tomorrow as we go over the test as well. This does not have to be a lab report. I'm not going to force you to write a lab report. However, if your lab report scores are lower than you would like, and you would like to write a lab report, then please do so. That I will grade it, and it will most likely improve your overall lab report score. Ms. Danita has a request for a trial.
No, I was waiting until you were finishing with the instructions.
Oh.
This part's just for fun.
Oh. So everyone give Ms. Danita a big hand.
Yay.
Yay.
All right, but there's a request. What's the request?
I just really want to see what happens. So the first question of the analysis says, well, you conclude about the time it takes for two solid spheres of different diameters to roll down the same incline. And I thought that the two marbles at the beginning went really quickly. So I kind of want to see what happens when you do a really tiny sphere and a big sphere.
Okay, so we've got the lacrosse ball, and we have the super small marble. So one last trial, and then it's lunchtime.
Yeah.
All right. Predictions.
I don't know.
I don't really know, but I'm about to go with
I'm going for the small marble.
Okay.
I vote small marble.
3, 2, 1, go. Small marble wins.
Woo!
Yay.
Good job. All right.
That looked more like a tie than a win.
I was slight win. All right. Take
Bye.
care. Stay healthy. See you tomorrow.
Okay.
Get some sunshine before it rains again.
We'll try. We'll try.